So everybody, welcome to JP3's first global webinar. This is on real-time analytics. What if measuring hydrocarbons could be quick and easy for your business? So just a few words on JP3. JP3 is a wholly owned subsidiary of Flotek Industries, an NYSE listed company. JP3 is a leader in the oil and gas measurement and analyzer market, serving the upstream, midstream, and downstream segments for real-time process control, quality monitoring, and custody transfer. JP3's game-changing analyzers provide real-time information that enables customers to maximize the value of their hydrocarbons. This presentation has been put together by Making Measurements Matter. So M3 is dedicated to education related to measurement solutions globally. So that's everything that you were sent, all of the communication with me, all the sort of technical bits. This is still a JP3 real-time analytics webinar. And then our speaker today is Mr. Harris. So that's Phil Harris. Some of you may know him. Please feel free when he'll pop on probably in about 2 minutes. Feel free to say hi. He'll be happy to see you guys all here. Phil is the president at Insight Analytical Solutions, which is a Calgary-based integrator, distributor and developer of process analyzer and sampling technology, Bachelor of Science in Physics, Master of Science in Chemistry, 35 years experience, starting in the nuclear industry and coming to Alberta to develop process analyzer solutions for the oil and gas industry in 1993 with Western Research. He's a fellow of the ISA, recipient of Lifetime Achievement Award for Technical Innovation, the ISA Award of Excellence in Technical Presentation, and a 7-time recipient of the GTFK Award for Best Technical Paper. He's the author of over 30 technical research papers and used to travel internationally to teach courses and design process analyzer sampling systems. FYI, everyone, it is 4 o'clock in the morning here, and that was a lot to say. So thank you very much. If anyone has any more questions on all of the parties that are taking part in this beautiful presentation today, please let us know. Our friends at JP3 are here, Phil is here, and we are here for you on a technical side. So without further Chelsea rambling, I'm probably going to welcome Mr. Phil Harris to the stage. Phil, are you there, my friend?
You are muted, Phil. We cannot hear you.
God, I thought he wasn't coming. Jimmy, thank God for you. I was like,
come on. I'm just gonna talk to a dead mic for a while, Jeannie. Hi, Jeannie. Good morning. Hi, Chelsea. Thanks so much for your help. I'm sure you guys have been well taken care of. I always like to thank Chelsea and her team. They helped me set up all these webinars, all the online training I do, and just take care of the crowd for me. And as you can see, generally things run pretty smoothly with these things. Thanks for the introduction again, Chelsea. And yeah, welcome here. God, we got several JP3 people here, Greg, Coyd, JZ, lots of clients I see here as well. Ravi, good to see you, man. It's been a while. Anyways, yeah, so we're gonna get started.
Note, I'm sorry, Phil, to interrupt you. Just a quick note for anybody that's watching through the Skype group, you'll have to type, please, and Jeannie is going to have to say it. I was going to try and hope to jump back and forth there, guys. And sorry, Phil, for the technical bits. But no. Jeannie, please just pop in and interrupt and ask the questions that are present in that Skype group, love.
Yeah, sure.
Sorry, hit it, Phil. Pardon me.
Thanks. No worries, Chelsea. Thank you. Yeah, so we're going to go ahead here and see if we can get this all moving. So as Chelsea said, we're going to be talking about JP3 measurements and real-time analytics, primarily focused on the oil and gas, hydrocarbon processing kind of sectors. And so we're going to try to give you a bit of an overview of the technology itself, and then talk about some of the applications that we're currently doing, and stress to you at the end that we're open to other applications as well. So kind of the agenda for today is, although Chelsea has given you a bit of introduction to everybody, I'm going to start off also with a little bit about, kind of who are we, who are the players involved here? And I like to put things in terms of questions because, that's what we're really all here for. As part of this measurement community thing, what we want to do is identify what are the things we can do, how we can do things better, how we can learn more. So I like to put things as questions and then try to pose those answers to you. So we're going to talk about who are we, we're going to talk about what's new, We're going to talk about what works and proven applications of this new infrared spectroscopy technique. And then we'll talk about what next and how you can find out more. So as far as who we are, as Chelsea said, there's kind of three players here right now, if you like. JP3 is, as Chelsea mentioned, a subsidiary of Flotek, and it's an equipment and information company that develops and sells online analyzers and data analytics. And so, they do a cloud-based data platform where you can see real-time what's going on in all of your processes that are being monitored by this technology. And JP3 brought to the industry really a new kind of unique measurement technology that enables radical efficiency improvements, and especially in applications where traditionally it's been difficult to put analyzers because they're being installed in remote facilities. Insight's a Canadian company and we work with them. And so a lot of our installations are up in the far north. There's not a lot of instrument technicians there. Often if you want a guy in, it's 6 or 8 hour drive. So one of the unique things about this technology is the fact that it has almost no maintenance. So Insight, we've worked with JP3 since 2013, I think. I started doing consulting work with them, and then we helped bring this technology to Canada. And Insight's a systems integrator, distributor, and a technology development company, and JP3's business partner. And as Chelsea mentioned, Making Measurements Matter is something we've been working to put together to try to bring educational seminars, webinars, and training to the measurement industry globally. So what's new? What's new, what we want to talk about when we talk about what JP3 brought to this technology is improvements in near-infrared spectroscopy. How to do those sorts of measurements more reliably, with better resolution, higher precision. So basically, we're going to talk about better spectrometers. Then we're going to talk about improvements in chemometrics and more robust algorithms and how we can take that spectroscopy data and analyze it. And then we're going to talk about improvements in sampling and how we've reduced the issues that occur in process analyzer sample systems. So the first thing I want to talk a little bit about is just the type of spectroscopy we're using here. And so for those of you, I'm a spectroscopist by trade. So to me, this always seems like it's second nature. But I like to try to put a bit of an explanation into this for how spectroscopy really works, and specifically kind of how absorbance spectroscopy works. Oops, let's change my pen color here. What color am I going to use to write on red? Oh, I'm going black. Okay. So when we talk about absorbance spectroscopy, what we're talking about is shining a light through a sample, as I'm trying to indicate over here, and seeing how much makes it through on the other side. And so at first glance, you might think, well, if I wanted to determine how green something was, I would measure how much green light it transmits. But a clear glass window transmits green light as easily as a green piece of colored glass does. The difference is the green piece of colored glass transmits green light, but it blocks blue and red. So when we look at something like some green food coloring or a green piece of glass, we see it as green when the light shines through it because it stopped the red and the blue. So this is what I'm trying to show here, is that it transmits green light and it blocks the red light and it blocks the blue light. So we can identify that something is green by looking at how much blue and red it blocks. And that lets us figure out what colors it's actually transmitting and how we would see it. The problem is when we start looking at some hydrocarbon samples like crude oils and things like that, they don't transmit very much visible light. So we have to start looking into different parts of the electromagnetic spectrum. We look at different wavelengths. And so what I'm trying to show here is that if you take something like, let's say, a crude oil, and you try to shine visible light through it, it would absorb and block almost all of that visible light. This is This isn't a crude, it's a natural gas condensate, but it's a heavy condensate right off of a condensate stabilizer. And so you can see it doesn't transmit much visible light. It's very dark. But as we go beyond the red end of the spectrum, and we get into what we refer to as the near infrared, near because it's near to the visible, infrared because it's beyond the red, we start to get less and less absorption, and basically more light makes its way through. And there's a couple of places where it starts to absorb some light, or the hydrocarbons absorb light. But once we get out to about here at about 1600 nanometers, that's where all the magic starts to happen. We start to get all of this absorption of light again. And from the pattern and shape of that absorption, we can identify what hydrocarbons are present. And from how much of the light's been taken away, we can identify how much of those hydrocarbons are present. So we can do qualitative measurements, what chemicals are there, and quantitative analysis, how much of them are there. So this isn't new, okay? This has been, infrared spectroscopy has been around for a long time. Koblenz around 1900 built a big spectrometer the size of the room that I'm in, and he was using it to look at the infrared spectra of different hydrocarbons, and he was basically the first person to come out and say, you know, none of these hydrocarbons, as we change the shape and the number of molecules that are in them, the spectrum changes, and no two spectra are the same for two different chemicals. So we show an example up top of gas phase methane and gas phase ethane, and you can just see how differently structured their spectra are. Around the 1950s, people started to try to apply this technology to actual process measurements, especially for things like determining water content in things like food, in things like oils. They would look at how much light gets absorbed by water at a certain wavelength and identify how much water was there. In the 1980s or so, fiber optics became more popular, and people started developing FTIRs or FTNIRs. FT stands for Fourier transform, NIR, near infrared. It was a great Canadian thing. There's a company out of Montreal called Bowman. They later got purchased by ABB, but they were a big foundation of the development of a lot of this technology. And it got applied in petrochemical plants, in refineries, but there were always places that had a lot of maintenance technicians that could deal with the fact that these analyzers typically required a lot of maintenance, and that these things had moving parts and, you know, were just not necessarily extremely robust devices all the time. There was difficulties with calibration transfers and a lot of things that had to be overcome. So JP3 started, you know, in just after 2010, 2011. And it was based really on, first on looking at a new type of spectroscopy or a spectrometer, still near infrared spectroscopy, but using a new type of spectrometer. And was one of the things that they've really brought to this now is the first thing I want to talk a little bit about is kind of doing the spectroscopy a bit better. So there's a few things that allowed this to happen. The telecommunication industry was starting to boom and thrive. And of course, that meant we used lasers over fiber optics to transmit data. And this led to the development of a lot of work on distributed feedback type lasers and bright, intense light sources that were extremely monochromatic, all one color. They're extremely bright, and they could be made and mass produced to be very similar. As the telecom industry expanded, they said, we want to be able to run more than one color of light down the fiber. We want to be able to do different wavelengths. This is important to us because we want to be able to look at different wavelengths or color of light and see how much light's getting absorbed there. So the fact that they could change the wavelengths, tune these lasers, meant that we could start to do spectroscopy with them. The lasers that were being developed were being designed for telecom applications, long mean time between failure, robust, reliable, and very repeatable devices. So we started to be able to look at putting almost an entire spectrometer onto a device that is built in much the same way as we build silicon wafers for computers. This is kind of a pick and place thing with micro soldering basically, but then they're put onto the substrate, but we can build the core of the spectrometer, the thing that tunes the wavelengths around this very repeatable, manufacturable device that allows us to change the wavelength of the laser and run across the spectrum. And so, this is an example of kind of a packaged version of that with you like, and the light comes out over here on a fiber optic. So this allows us now to scan the laser and look at different wavelengths, and that lets us measure an entire spectrum. So when we look in the near infrared, we want to talk a little bit about, well, what do we see? If we take that laser and we scan it, I know it's hard to see here. So if we scan it from about 1350 nanometers out to 1800 nanometers, we get an entire spectrum. Oops, I'm just going to go back for a second and come back into this, as I want to talk about this top spectrum. It's going to automatically update after about 30 seconds. So the top one is a sample of a natural gas liquids. The bottom one is a sample of pure propane. And to the naked eye, our pattern recognition skills are pretty good. We can tell the difference between those. You could look at those and say, I can tell the difference between propane and NGL. I can tell the difference between propane and N-butane. I can tell the difference between propane and isobutane just by looking at the spectrum. Where it starts to get complicated, though, is in the real world. We end up having samples that have a mixture of components there. So now we end up with something like a stabilized condensate or a natural gas or gasoline, and it has a mixture of chemicals, and all of those spectral features, spectroscopists often refer to them as fingerprints, all of those spectral features start to overlap on each other. And suddenly our naked eye visual processing isn't so good at determining what's there. But another enabling technology which has been developing over the last decade or two has been the things that we can do with pattern recognition. So in chemistry, we refer to it as chemometrics, and it is the art, if you like, of using numerical analysis, using the ability to look at patterns in data, and from that extract meaningful information. Chemical composition, physical properties. So the enabling technologies that have allowed us to improve how the chemometrics is done has been the massive advances we've seen in computer speed. They talk about the speed of computers doubling every couple of years. My cell phone now has, infinitely more computational power than the first personal computer I had. So we have these very fast computers. We have a lot of industry is looking at how to use patterns and shapes to do certain things. The example I'm showing there is face recognition, but we do it fingerprint recognition on our phone now. We do voice recognition regularly. When I was going to university, in the long time ago, you don't get white hair like this for nothing. When I was going to university, artificial intelligence people were saying, well, we don't know if we'll ever fully be able to interpret human speech with a computer. Well, of course, kids' toys do it now. So we've seen this ability to take patterns and waveforms and make it into actionable data. So that's what we do with chemometrics, is we apply that pattern analysis chemistry. We use the spectral data, the shape of that curve, to determine chemical compositions and or physical properties. So by combining the improved spectroscopy with better chemometrics, we can get better information. So those two pieces really enable us to take the spectra that we measure and make it for information. But what we know in the process industry is that one of the big difficulties is, how do we get a good sample to the analyzer? And how do we keep the analyzer up and running? Sample conditioning. So one of the things we had to consider then also is, how can we make that whole process of having a sample flow over to the analyzer easier? we say 80 to 90% of the problems that happen in analyzer systems are related with sample systems and trying to get the fluid to flow through that product. And so what we want to do then is try to minimize the complexity there. We want to minimize the amount of filtering we need. We want to minimize the use of regulators, valves, and small tubing. That helps reduce all of our maintenance requirements, keep everything as simple as possible. And then we want to take that solution and close couple it to the process we want to measure. And that allows us to get faster response times. Faster response can often lead to better process control. So what I'm showing here is a typical sort of analyzer sample system. And this is probably not a typical GC oven, but it's the sort of thing we see in GC ovens. There's a lot of small tubing in there, complex flow paths, potentially difficult to maintain. We certainly have to do a lot of training for instrument technicians to work on these things. So what if we could make this simpler? What if we could make it so that we have a flow cell that has all half-inch ports? So all of our flow paths can be on half-inch tubing and half-inch pipe. What this does for us is gives us large diameter of tubing, large diameter piping that is going to be less likely to plug by the dirt and the wax that might be in something like this. Inside that flow cell, we have ports so that the fluid we want to measure can flow through it. And into that flow cell, we put 2 sapphire cores. We use synthetic sapphire. It's the second hardest thing next to diamond. So I'm going to make sure I can see this. So this is an example of a cutaway of the flow cell.
So
Bill,
I'm jumping in. I'm sorry. So everybody, this would be a good time. You know that little toggle I was telling everybody about? If you want to see what he has in his hand a little closer, you're just going to stretch that to the left and minimize the presentation. And then you're going to see a big fill and everything that's in his hand. There you go.
That's what everybody needs is a big fill. So we've got this large flow path. We can run process fluid right through there. And so the fluid I want to measure is running between those 2 sapphire rods. The other beautiful thing about synthetic sapphire is it is, even a large thick crystal like this is crystal clear. And so it allows light to transmit it. And especially important, it transmits infrared light quite well. The way this cell is constructed, it's been tested up to 10,000 PSI. Is that right? 15,000, actually, sorry. We have a registration in Canada, so a CRN number for Canada is to 1,500 PSI, and that was basically based on a test that tested it to 15,000 PSI. So we can handle process pressures and process temperatures without any sort of pressure reduction or relief valves and things like that. So now we can say we're going to take exactly what is the process fluid and run it through this sample cell. As it runs through the sample cell, the light from that new spectrometer comes in over a fiber optic and shoots through the sample and gets picked up on another fiber optic and taken back to a detector. So we've addressed one of, or a couple of the issues with sampling here by having large ports that are difficult to plug, and we actually don't need to filter the sample. We don't put any filters in front of these typically. We allow the sample directly in its native state to flow between there. So this lets us kind of change how we approach measurement, if you like. We take a process pipe, put a probe into it. We look for some source of differential pressure. This could be from an orifice plate, could be a control valve, could be a pump. It could just be a low pressure return someplace. We look for some source of differential pressure. We want to use process differential so we don't have any pumps in the system. We mount that cell as close to that process pipe as we can, and the differential pressure runs through some half-inch tubing and drives flow through that flow cell. So we have the flow cell, and then remotely, we mount this analytical device that contains a spectrometer, and we connect it by fiber optics. The fiber optics shoot a beam of light out through the flow cell and return it back to the analyzer. I kind of view this as, this is where the actual measurement happens. It's where the light interacts with the sample, and this is where the brain is. Because no process fluid runs back to where that brain is, we don't need any specialized analyzer buildings or shelters. We can mount this in an MCC building, in a control room, in a blending skid room, and put the brain part any place because we don't bring process fluid back to it. This minimizes risks to our staff. We don't have sour gas or sour liquids coming to it. We don't have hydrocarbons coming back to it, so we don't need gas detection and protection against possible combustion. And so now we bring that information that happened when the light got absorbed by the hydrocarbon back over to the brain. We measure that spectrum, and we use those chemometric algorithms to convert that into actionable data. We look at that spectrum and we say, this is the chemical composition. C1 through C6 plus, C1 through C9 plus. These are the physical properties: vapor pressure, BTU content, API gravity, cloud point. We can do this in gases or liquids. The same technology can be applied to pretty much any type of fluid, from a light NGL to a natural gas to a crude oil to a natural gas condensate. Not only that, it does this fast. We can get this entire analysis done around every 15 seconds. So we get a new data point, a new update, if you like, of our information quickly, much faster than we would get, say, with a conventional chromatograph or physical properties analyzer. And that close coupling it to the probe makes sure we get, or to the process, makes sure we get fluid there fast. The data analysis is quick. So now we get near real-time data for process control. The brain is also smart enough that it can handle more than one of these cells. So this one might be up here measuring crude oil. I could run another set of fibers out and bring it over to this flow cell. And this one might be measuring natural gas.
Hi, Phil. Sorry to interrupt you. We've got a question in the chat.
Mm-hmm.
Okay, perfect. So I'm not sure who it's coming in as Sandy one. So Dave,
Okay.
not Dave. Sorry, guys. This isn't if this isn't clear enough for you, please pop off mute and just get some clarification with Phil. This is not my field. So if delta pressure across flow cell is higher than delta pressure in main process line, how the fluid will be returned back? How does the fluid return back?
Yeah.
Okay.
So yeah, I mean, we certainly, that's one of the things that we have to look at when we do an application review, if you like, is what's the pressure? I need to know the pressure at the sample point. So call it P1, and the pressure I'm going to go back on my return point, if you like, P2. And we need to ensure that P1 is always greater than P2. So we need to have that. Well, actually, I suppose that's not even really true. It's just ideal. If P2 became greater than P1 for some reason, we would just get flow in the opposite direction through the flow cell. But it's basically an unrestricted flow typically, without necessarily a flow limiting device there. Ideally, if we are going to put a flow limiting device like a needle valve in here or a flow restriction, sometimes what we do is we just run narrower tubing on the return side. We would put it on the downstream side for a liquid because we want this cell to stay at pressure. Keeps the bubbles in the liquid so we don't have any bubble issues. We have to still have to look at applications. This analyzer is designed to make single phase measurements. So if you're going to do a liquids sample, it should be all liquid with no gas bubbles. If you do a gas phase sample, you prefer it to be all gas phase with no liquids there. I see also in the chat, we have a question. in regards to temperature variations of the process on the measurements. And certainly I know Jay-Z is on here, and he's one of the spectroscopists with JP3 and can certainly probably address this in more detail. There is some temperature variation in the near infrared spectrum that if processed fluids are changing temperatures dramatically, the spectrum can change shape slightly. And so the way we attempted to address that is by building our models, our chemometric algorithms, based on samples that have been run at numbers of different temperatures. So we continuously monitor the temperature. So we know if we're in the range of temperatures that we've built our models for. And we try to get samples and data that encompass that temperature variability and allows us to flesh out our models a bit to deal with the fact that the spectrum is going to change a bit, or spectrum may change a bit with temperature. And if what I answer, by the way, doesn't completely address your question, feel free to jump off of mute and ask, or send something to Chelsea or Jeannie and ask for more clarifications.
Thanks,
Joe. So there's really three flavors of this analyzer, if you like. There's a simple one that can measure a single stream. And so we tend to use that on things like a crude oil blending skid. There's another version that can measure up to 4 streams, and that's the most common one we see going out there. And there's another version that will even go up to do 8 separate streams. So if you were doing a full fractionation plant, you're probably considering a 4-stream or an 8-stream analyzer. Because the data is acquired so fast, even with 8 streams, if we're getting an update on each stream every 15 seconds, so what we do is we measure on one stream and then the next and then the next. So if we're getting an update every 15 seconds, it's 2 minutes cycle time to measure all 8 of those streams. So this ends up making our installations quite simple because we don't have a lot of equipment in the sample conditioning side of it. So I show a typical PID. Hopefully this shows up well over the screen, and AutoCAD drawings and all those skinny lines are often tough, but we have a sample point here with a double block and bleed valve or assembly. We come in, we go past a flow transmitter, flow through the flow cell, we have pressure and temperature, return back to the process. So that's our complete flow path. Now we may add things on there like lab grab sample points, and that's typically what we do. So, this is probably a simplified version of this P&ID, and I'm going to show you an actual cabinet in a minute. But then we run fiber out from wherever we put the analyzer. So our fiber optic comes in, and in this case, we often will say we'll put it in something like an electrical building, an MCC building, a control room, any place else. Again, no process fluid is coming back. All we have is fiber and some analogs and some digitals. So some communication that goes back and forth and fiber optic connection. So this is an example of one that's sitting on a crude oil blending skid. So they're blending crude inside this building. So basically this is a crude blending skid. They're putting butane into crude oil. Butane is a lower cost product. And so if you can sell butane as if it were crude, there's economic value in doing that. If we can sell a low cost product, I put it as, it's similar to, adding any lower cost product into more expensive products. We take it and we blend in something like ethane into propane or butane into crude, because we can take a less valuable product, blend it in, sell it as a more valuable product. But we have to ensure we hit specifications. And in this case, their specification was based on vapor pressure. Oh, sorry, excuse me. Hit the wrong button. There we go. So this crude is coming out. It flows past this yellow device that you see right there, which is our flow. The infrared cell is right here. Temperature, pressure up here, and then our return back to the process over here. So just to let you see this maybe a bit better. So we come in on that bottom valve, flow past the flow switch, flow up through the infrared cell. You can see the fibers coming into it from either side. And then we flow past the temperature and pressure transmitter and return back to the process. It's our entire sample system for a crude oil blending application. This particular installation is in South Saskatchewan in Canada, fairly heavy crude. They're putting blending depropanizer bottoms into it. Ran for 9.5 months. We were questioning whether they were even looking at using the data because we didn't hear anything from them. And my service technician gets a call on a Sunday night and we just lost data communications to the analyzer. Can you help us figure out how to get Modbus communications going in? Cell was never cleaned. It's been, and they're reading vapor pressure continuously all the way using it for continuous blending. We keep the flow path simple. This is on a condensate stabilizer, a gas plant. So there's a control valve down there. We come off the high pressure side of the control valve on the green line, flow through that little cabinet that's there, come out, return back over the process on the low pressure side of the control valve. We put this measurement right out as close to the process as we can. This is another crude oil blending. We have crude oil flowing through this pipe down here. The infrared cell is sitting right here. We take a sample of that crude oil, run it through the infrared cell, return it back to process. And so we've mounted the analyzer and the flow cell as close as we can to that blending skid so that, again, they get real-time data to control that skid. Another this one's on a de-ethanizer. So the de-ethanizer tower is sitting right over here. We mount that panel as close as we can. Short sample lines, fast response time, less places for things to plug. So closed coupling, keep everything simple. Short lines, it's fast. Really simple flow paths for technicians to understand and look for any potential issues in. Large bore tubing, no plugging. Minimize all of our installation space, and we don't need any analyzer buildings. No fluid is running back to the analyzer. Put that picture of the mountains up because out in the mountains this weekend and you got to see all the snow there. And I know we invite a lot of our colleagues from the Middle East to this. So this is another installation out in Canada. And so again, you see there's that cabinet sitting out there in the middle of the snow. You open up the cabinet, very similar to the other one we had. Flow transmitter, infrared flow cell, pressure, temperature. A couple of bells and whistles, features added into this one. So sitting out there right in the middle of the plant. The analyzer is mounted over here in an electrical room, MCC building. Analyzer mounted on the wall. Inside the analyzer, we have the spectrometer down here. We have a PLC that we use for all of our data communications. And there's a single board computer in there. I'll just take my ink off of here and zoom that for a second. So it gives you an idea of, again, there's not, there's a lot of intelligence and a lot of capabilities in this device, but from a complexities perspective, we have a PLC, we have a single board computer, and we have this tremendously intelligent and fast spectrometer. And we take all that, we mount it in the MCC building. You can see there's electrical connections and fiber optic connections coming down in from the top of the cabinet. And this one's on a condensate stabilizer. So it's running heavy, thick, waxy condensate like this. This is a facility where they've had lots of problems with analyzers because of the wax content of the high molecular weight alkanes in these condensates in northern Canada tend to plug a lot of sample systems off. The wax just builds up over time. You can actually see we put a little heater around the cell. We put the cell inside of a heated box. We keep everything above the process temperature by a bit, and that prevents us from getting those wax issues.
Excuse me, Phil, there's a question in the chat. This is from Guy or Guy. Is it a pre-confirmed PLC, or can you put this into an existing PLC?
We pre-configure the PLC to add in all of the the hooks, if you like, for how to communicate to the spectrometer. And also it does all the Modbus communications, say back to your DCS or your PLC or any other control systems. However, we can also add customization to that. So if, for example, we have a client such as yourself who says, you know, I'd like the analyzer, if it reads high on butane, to automatically shut this valve, or things like that, we frequently add and reprogram that PLC and customize the user interface of that PLC to ensure that people get the information that they're looking for. But we do require that there's that PLC there, because that handles all of the low-level communication stuff over to that single board computer. And it's an Allen Bradley, we typically use Allen Bradley PLCs in there.
And another question.
Yeah.
Oh, okay, thanks. Thanks, Guy. And by the way, sorry, that was from Lamad LLC. Analyzer samples. Okay, so this is from Asik Kumar Hazra.
Yeah.
Analyzer sample cells, etc., are put in open air.
It depends. Our friends here down from JP3 are down in Texas. And so it doesn't get really cold at night. And they tend to, a lot of their installations, the analyzer sample cell is actually just put out into the open air. When we get to conditions like we have in Canada, where, you know, we have to design things for a minus 45 degrees C ambient, you know, that's the cold. And when we get into Northern Canada, the typical low temperature spec is minus 45 degrees C. We put it inside of a box like this one, so that, oops, not zooming, just a sec. And we put it inside of these boxes so that we can have an insulated enclosure around it and a heater inside the box to try to maintain that temperature up. If we were putting one in the Middle East, because of the big temperature swings from day to night and seasonally, we again would probably look at putting an enclosure around it to protect it from those big ambient temperature swings. And I apologize, I think I'm running a little bit long on this. We're a bit more than halfway through though. Certainly, if anybody has to leave because of time constraints, I apologize, and we will get a recording of this together. And I'll try to speed up a little bit. Hopefully that answered your question about putting it outside. In some applications we do. Typically, if there's large weather extremes like we have in Canada, minus 45 in the wintertime, plus 35 in the summertime, then we start to temperature control around where the analyzer flow cell is. The analyzer itself is rated from minus 20 degrees C to plus 50 degrees C, so it doesn't need a really well temperature controlled building. We can use these on multiple streams. So this, again, it's another Canadian installation. 4 streams: condensate stabilizer bottoms, nasty, dirty condensate like this stuff. Debutanizer bottoms, which tends to have similar chemical composition, but all the clays and waxes are gone, so it's nice and clear. Deethanizer bottoms and a C3 plus stream going over to storage. One analyzer that you see on the wall over here. So there's our brain. Oops, sorry, pen's not on. Here's our brain over here. So if we just zoom in on this guy.
No, we've got
Yes.
one more question in the chat from KC. Can the analyzer withstand potential exposure to seawater?
In the flow cell, I mean, certainly, like, I mean, the flow cell construction in all of our flow path is 316 stainless steel, synthetic sapphire. So the materials that come in contact with process fluids are certainly going to be resistant to chloride-based corrosion. You know, NYSE is a big thing for us. So if you're talking about, say, a briny crude that occasionally had slugs of seawater that came through it, it's not going to measure when the seawater is going through it, but it's not going to do permanent damage to the flow cell.
Awesome, thank you.
Okay.
Oh, one more, sorry.
NYSE is, I see it. Yeah, thanks, Chelsea. I got my other window at the chat up right now. So NACE is kind of a funny thing. NACE is often a self-certification thing, right? NACE, we provide a certificate of conformance. You know, we use all Swagelok components in there. I'll give Swagelok a plug because I see I got Thebot on here, and so I'm gonna make sure I give my colleagues a plug as well. No, we use all Swagelok components. So again, those all come with NACE certifications. Obviously, tubing has NACE certifications. The flow cell, it's like, so but other parts of the system can be a self-certification where you say the materials used are compliant with NACE. And so we look at it in terms of what's your stream composition? Are we using the right materials? And we provide a certificate of compliance on an integrated system. Cool. So you can see we've got the braid over there, and then we've got these panels on the wall. Oops, over here. I can't draw when it's up like that. And so this next picture just shows that there's 4 panels sitting there. Each of those are the flow paths for a different one of those streams. And so we are measuring all 4 streams with the one analyzer. We have it mounted in the same building in this case as this one. We didn't put the panels out at the process point because the customer said, we're already bringing process fluid into this building. So when we look at the comparison of how things have been done traditionally, with the near-eye infrared technology, we can measure right at the process instead of transporting a sample and measuring it remotely at an analyzer building. We measure at line pressures and temperatures, reduces our risk of phase change. If we put some complex sample conditioning systems in, we always have the risk that as we go across a pressure reducing device, or as we try to change temperatures, that we're going to have a phase change. All of our flow goes through 1/2-inch tubing or pipe on the NIR side, whereas the 1/8-inch or 16th-inch tubing we'll often see on conventional analyzers. No filters and regulators, no things that plug. We had a client who had an online vapor pressure analyzer and a chromatograph to measure, again, a dirty condensate. And he estimated his spare parts cost was $50,000 Canadian a year, plus the service time, changing filters, changing injection valves, cleaning components, etc. We get very fast response time, which can give us better control. We can make multiple measurements. We can use one analyzer and be doing a chemical composition analysis like C1 through C6 plus, and a physical property like API gravity or cloud point or pore point, or there's several physical properties that are well correlated with the near infrared, one of those being vapor pressure, which is a very common one that we do. We can mount the analyzer anywhere. We don't need a dedicated analyzer building. The detriments of the NIR is that we have to do modeling. So it's an inferred measurement, so we have to build a model. We have to take lab samples and build that model, whereas a chromatograph can do sort of direct measurements, if you like, of peak heights and peak shapes. And with the NIR, we generally don't go below typically around 1,000 parts per million or so. Whereas a GC or something like that, we can often do trace components. So you can see we have, yes? Yes, Jeannie?
Yes, we have a question.
Oh, thank you. Multi-phase streams, in case you keep, yeah, so multi-phase is difficult for any analyzer. You know, if there's bubbles in our liquid samples, because, you know, when we come off of tower bottoms, we're often right near the bubble point. So if the pressure drops, so we're dealing with this right now at an installation where the return point is at quite low pressure. So we have to put a back pressure regulator in that case, to keep, or a needle valve or something to keep the pressure in the flow cell. Generally, it's very difficult to do measurements on multi-phase samples. You have to typically try to do something to get it back to single phase. So pressurize it if it's a liquid, cool it if it's a liquid, heat it if it's a gas, and try to get it to be single phase. We are looking at an application right now where potentially we want to do some phase separation. Typically, what we try to tell our customers is, let's look through your process and try to find a sample point where we can get preferably a single phase sample. So from an applications perspective,
Yeah, we have two questions.
I'm assuming that's Verlesh Desai. Hi, Verlesh. I can't see the whole list here. Can it address all of the applications typically done by a GC? Not necessarily. Depends which ones we're looking at. Like on an ethylene furnace, you might be looking at things like trace acetylene and ethylene. You know, it's a common application for people to look to see if they're running their crackers well. So the trace component measurements would probably still be done by a GC or by something like a TDL. Again, we're typically doing bulk compositional analysis. So, you know, we could probably be looking at the ethane, ethylene, propane, propylene splits, but we may not get to some of the trace components like ammonia, sometimes of interest in ethylene crackers or acetylene. Those are probably still going to be done by another technology.
Bill, did you get the one above it as well? How about C6 plus measurement? If yes, what is cycle time?
Yeah, I can actually show some data on the next slide where we go all the way up to C12. And so it's a really interesting application. So I'm going to address that question with the next slide, if that's okay. So, you know, I'm not going to go into too much detail on this slide, but we basically have installations that sort of go right across the hydrocarbon processing market, from the upstream side, looking at crude oils near the wellheads, or looking at vapor pressure stabilization near the wellhead, through transportation and midstream to the downstream side, and same on the gas processing side. You know, we'll look at gas compositions at plant inlets, gas plant operations, condensate stabilization and fractionation and pipeline applications. So, you know, it always seems that when you get your first application, there's got to be something that makes it interesting. So one of the first applications we did, an engineering in Canada, an engineering company had come to us and said, we have a client and they want to measure butane in their natural gas condensate. So our quote was all based around, we're going to do a C4 measurement for these. I got a frequent calibration. I'll address that one as well in a minute. So we get it out to the client site and we talk to their process engineer and their measurement engineer, and they say, well, yeah, butane and condensate's the spec we have to hit. But what we would really like to get is a full C1 through C12 analysis. So from methane out to dodecane and vapor pressure. And we'd like to do all of that on the same analyzer, please. No hardware changes. Same flow cell, same spectrometer, same PLC. All it was building up additional algorithms and models so we could measure all those components. And so what I show up here are the results. They wanted to know the C1 through C4 in liquid volume percent. So there's three, A1, A2, and A3 are three different condensate stabilizers. We're comparing the results against lab results. And so you can see, you know, there's always differences from analyzers compared to labs. There's noise in both measurements. There's repeatability issues in both measurements. But you can see we have very good correlation across the board generally on the C1 through C4s. And when we take a look at the measurements going out, all the way out to C12 plus, we see that again, we have very good correlation on all three trains to what the lab was getting as compared to what we're getting on the analyzers. And so, and we do all this analysis in 30 seconds. So the question was, you know, how fast can we do a C1 through C6 plus? In this case, we're doing C1 through C12 and RVP in 30 seconds. So this analyzer that's at this facility is actually measuring their condensate stabilizer bottoms and their deethanizer bottoms. We do a C1 through C6 plus on their DF, C1 through C12 on their condensate stabilizer. As far as calibration frequency, so as I mentioned, we build models. And we do that by pulling lab samples. Oops, that place doesn't want to let me write. Oh, funny. We do that by pulling lab samples. And so once we've built a model up, the analyzer runs statistics that look at how well that model is, or how well the data processing is fitting the curves that it's seeing. And so we get that statistical analysis, and it allows us to say, well, the fluid we're seeing looks like it still fits within the model space. So we don't have to do any recalibration at that point. When we do recalibration, typically what it means is we pull additional lab samples, get them analyzed, use those lab samples in the spectra to update the models.
So there's a few more questions you probably saw pop in. I'm just going to make sure we've got them all, okay? If one's not relevant for now, just let us know and we can move on. Okay, so we left off at,
we did the frequent calibration was the last one.
And so one analyzer can be used to measure all the HC streams just to select which algorithm shall be used?
Yes, so one analyzer, the spectrometer, if we're using a 4-stream analyzer, it has 8 fiber optics, 4, I use simple terms, 4 goes out fibers, 4 launch fibers, and 4 return fibers. The spectrometer switches the laser between, it says, I'm going to go and send the laser out on fiber 1. I'm going to look at the data coming back in on return fiber run. I'm going to run this model and algorithm on that data. Then I'm going to switch to fiber 2. So fiber 1 might be my inlet gas. Fiber 2 is my deethanizer bottoms. Switch to fiber 2, run a completely different set of algorithms. Switch to fiber 3, run a completely different set of algorithms. And so it could be, one could be natural gas, one could be deethanizer bottoms, one could be product propane, and one's crude oil. So we can use one analyzer and measure all the hydrocarbon streams.
Awesome. And then how long does it take to fully model and fine tune a C1 to C12 application from start to finish?
The first one we did took us quite a while. It probably, we were going back and forth probably over the course of 6 months to see all of the variation they had in their problems or in their process. We've learned some things along the way and how to expedite that process. And also we even had to look for better labs and lab methods. And so now we just did one where we did the install last week and we, oops, my backdrop just went turned off. There we go. We just did the install last week. We had put an analyzer out there to do a bit of pre-modeling, and we're up and running and controlling their condensate stabilizer already within probably 10 days of installation or so. We'll add more data in. The models get better and better and better over time. The more lab samples we pull and add in there, it lets us flesh out that model space.
Brilliant. And then when you say 30 seconds, is it a batch analysis or continuous? Generally, you call T90 if it's real time.
Right. So T90 usually refers to the time to 90% response. The way this one works is a little bit different than what we think of in a lot of conventional analyzers, because we have continuous flow going through the flow cell. There's always fresh product there. We switch the fiber optics and shoot the beam of light through the flow cell and measure we add up a bunch of spectra. So we make a bunch of, and that can happen over the space of a second or two. And it's an instantaneous measurement of what's in that flow cell. There's not necessarily any averaging time constants in there. It's shoot the spectra several times, add the spectra up to get signal to noise up, and then do the analysis. So it's like a point measurement that's done every 30 seconds.
Brilliant. And if anybody needs any more clarification, guys, please jump off mute and ask Phil. He can explain further if you need to, or if he needs to, or if you need him to. And then finally from Elizabeth Jacob, can we measure HCs plus total sulfur plus?
Recaptants.
Thank you.
Yeah. If I get asked this question a lot, can we do H2S in crude? Can we do total sulfur and low level total sulfur in crude with this kind of reliability and repeatability? If I joke, usually I tell people if we could do that, I probably wouldn't be here giving this presentation. I'd be retired on a beach in Maui someplace. I mean, it's a very valuable measurement. And it's one that's difficult to do with spectroscopy because some of the sulfur compounds aren't very good absorbers. Some of the sulfur compounds are heavily overlapped by other compounds, and always the sulfur compounds are there, at typically trace levels. Condensate, we have a sulfur spec for of typically 10 ppm here. Even crudes, it's typically under, it's in that 0.1 weight percent kind of range. And so it's typically pretty low for us to do with this technology. So my answer would be, unfortunately, Elizabeth, I'd have to say no, if we could do the sulfurs.
Okay, and we have a few more. Can I keep going, or do you?
Yeah, yeah, no, it's great. I love questions. It's
brilliant. Okay,
yeah.
Well, the coating on the flow cell with time going to affect the reading. How do we overcome? And do we need cleaning and or recalibration?
Yeah, a good question. So, the optical surface is that flat window there. And so there's a couple things that we try to do. We try to keep enough flow going past that flow cell, so we have enough velocity that the particles and things that are going to coat on the surface tend to want to keep on moving with the flow. The laser is quite bright. And so when we get a coating on the surface, it blocks light, but it generally blocks all wavelengths of light pretty much equally. It doesn't give us that pattern that we see associated with the hydrocarbons. So what we see is over time, if the windows are getting dirty, is the light intensity starts to drop and decrease. We constantly measure that so we can give you a warning that says, your light intensity is decreasing, your flow cell's probably dirty. Somebody should go out and clean it. It's really 4 bolts on either side, and you can pull this flow cell apart. My technicians in the field generally keep some brake fluid around. Sapphire is the second hardest thing next to diamond. You're not going to scratch it. So they take a cloth, brake fluid, clean the cells, the windows off, put them back in. Does not affect calibration.
Awesome.
We've also done systems where we had a client who said, I don't have somebody there always to do that. So he was worried about wax buildup on the windows. So we built him systems where it monitors the transmission on the flow cell. If the transmission drops too much, it back flushes the system with toluene to get the wax out and then goes back to measuring.
Brilliant. And then Verlash, does the analyzer do the switching of samples, or does it have to be done by customer's DCS? Does the analyzer identify which stream it is analyzing?
Yeah, so we typically set it up. The standard configuration for a multi-stream analyzer is that the analyzer switches from which fiber optic it's measuring off on a time sort of synchronized basis. So it might be saying, okay, I'm going to measure stream 1 for 30 seconds, and I'm going to measure on stream 2 the next 30 seconds, then stream 3 the next 30 seconds, then stream 4. We can adjust that timing. So if it was stream 1 was the most important thing, you could say measure stream 1, measure stream 1, measure stream 1, measure stream 2, measure stream 1, measure stream 1, measure stream 3. So we can control all that with the PLC. What we use is different Modbus registers for the data results from each stream. So the DCS or control system pokes and reads the Modbus registers for the last reading that was obtained on a given stream. So of course we provide a Modbus map, say this is how you get your data.
Awesome. And any distance limitation on the FO cable?
Physically, not so much. And JZ, feel free to correct me. Physically, not so much, but we use a custom fiber optic cable. It has to have very low absorbance in the near infrared. We use a multi-mode cable on the return side. And so there's a cost limitation where it starts to get to the point of, if you're going to go that far, you're almost better off putting a second single stream analyzer out at that sample point. So physically, I would say that within practical, the longest run we've done in Canada is about 330 meters.
Great. How do you deal with aging of source and detector in the terms of performance delivery? In terms of performance delivery, do you have a reference channel?
That is, I could do a whole presentation on how that spectrometer is built. It is I mean, I'm a spectroscopist by trade. That was kind of where I cut my teeth in my career. And this is a pretty cool little device. So it has a built-in reference channel to look for degradation of the intensity of the light source. It has 2 temperature-controlled and built-in fabric pro interferometers that are being used to do a precise wavelength calibration of every scan. There is 0 wavelength drift on this spectrometer. Not only that, when this is what we just did at this plant. We put a different spectrometer out there completely, built some models while we were fabricating their actual system, and then we put their actual system in and just said, okay, just take the model off the other one and pop it in on this one. Model transfer is perfect from these spectrometers. They are precisely calibrated, all with internal wavelength reference sources, and it from a nerdy guy with a little spinning thing on my head, it's a thing of beauty. It really is.
Okay, as has from Burlesh, has JP3 supplied for natural gas metering application measuring N2 and CO2, including the HCs? Is there approval of product for metering application by a third party?
So N2 is one of the chemicals that what's referred to as homonuclear diatom, anything that has 2 atoms that are the same, N2, O2. N2 is not a near infrared absorber. So we have systems where we've built models to predict N2, but they're based on kind of like the historical data that's been seen at the facility. So CO2 is a infrared absorber. So sufficient levels of CO2, like we said, if typical Canadian natural gas spec is 2% CO2, at those sorts of levels, we can measure the CO2. There isn't a full third-party approval. There was a test that was done, I believe it was Southwest Research. Again, JZ, you can probably correct me here. There was a test that compared the accuracy and repeatability specs of the NIR to those that were necessary for a chromatograph. And there's also the Gas Processing Association, the GPA, is working on a reference method around using NIR spectroscopy, but there's not a full 30-party approval that I know of as yet. Certainly we don't have, in Canada, you have to get Measurement Canada approval. And we don't have Measurement Canada approval for pipeline quality natural gas metering. Greg says Southwest Research, yeah.
Awesome. And then everybody, thank you so much for your questions. If it's okay, Phil, can we proceed? And we'll get all the rest of these questions at the end. We just want to make sure that we actually cover the rest of the presentation.
Sure. Yeah. Okay. Ravi has one more. I'll just address it. Usually we do all the chemometrics, Ravi. JP3 keeps a fleet of chemometricians on hand, and we have cellular communications, all the analyzers, so we can pull data in and build models remotely. This is a truck offloader. So again, so you can see, so this is a truck in system. So now we're not getting continuous data. We have trucks that come in, they offload. Our customers said, I want real-time data for what's the composition, what's the flow rate. Now I can get a flow weighted average of the truck and what it's worth. And so you can see the difference that happens from one truck to the next. Here's a truck offloading that is fairly low in propane, but reasonably high in the butane. And so compared to the next truck that came in, which had almost similar propanes, much lower butane values. And so what they're using this for is, what's the value of that truck? I get a full C1 through C9 plus, they update once a minute, they take a flow number once a minute, and they construct a flow weighted average of a 1 hour truck offload. From an installed basis perspective, there's about 225 installations and over 600 measurement points in North America, all active regions and basins. As we sort of mentioned in the email, this is a beginning of the, JP3 has been strategic about this and said, we're going to install these applications close to home where we can support them, get data across a number of different basins, and is now beginning at taking this out to more international markets. So typical things that we'll see, again, I'll go through these fairly quickly. We'll do natural gas plants. So we can do everything from the rich field gas coming in, the dry sales gas, condensates, what in the US they call Y grade. Up here we call a C3 plus stream or an LPG stream. So we can typically handle most of the products that are being produced there. If there's a deproper or a deethanizer there, we can handle the bottoms and the overheads of those. Typically doing a C1 through C6 plus BTU relative density, vapor pressure measurements. Big advantages are energy contents, fast response, low maintenance, replace multiple analyzers with one technology. Frac plants, very similar things. We can do the NGL coming in on the inlet, the natural gas liquids coming in on the inlet, deethanizer, depropanizer, debutanizer purities. We can look at the butane splitters. We can look at the C5 plus streams. And again, it's this low maintenance thing that a lot of our clients look at it and just go, it just means I can have my instrument technicians working on some of my other problems, and this one just runs. And especially like things like these, looking at your debutanizer mixes and looking at your C5 plus streams, a lot of these are some high value products. Again, sort of just some data on a frac plant, and was one customer that sort of estimated, this was in the US, they estimated they could save about, or they could improve their performance by about $14 million a year just through better measurement. So when we talk about making measurements matter and why we want to do measurement, this is why we want to do measurement, because oftentimes we can find a way to optimize the process and get better data.
Hi, everybody. There's some questions up in the chat. Is it all right, though, if we move? I'm wondering about timing and making sure that we get through the presentation and touch on the applications and get where are we at with everything, Phil? Do you want to take these questions or do you want to wait till the end?
I actually like questions. We have, slides. I can talk about slides at any point. People can get a hard copy of the slides too. So I'll mention here that we do a lot of work with transmix. We look at products flowing down pipelines. And so the big thing here is that there's a transition between two components. And so we can use the analyzer to monitor, are we on spec for component one? We go off spec as the two are mixed. Are we on spec for component two? The stuff that's off spec, we're putting to storage. And so that has to be reprocessed. So there's a lot of money to be printed by optimizing transmix. Couple of questions. We can't build models based on customer data or customer compositions. We build models based on field results. You could run redundant fibers. Generally, once they're like a premature failure thing. If they get damaged during installation, they have to be replaced. Once they're in, we've not had issues typically with fibers that, we've had very few issues where we've had to go out and replace a fiber. TVP versus RVP. We can do VPCR4. We can basically, whatever lab result you give us, we can build the model from the spectral data to that lab result. So if you want to do TVP and you've got good lab data, problem with TVP, especially as some people define it, VPCR at a very small overhead volume is it's not a very repeatable value as compared to something like VPCR4. So VPCR4 at 4 expansion volumes tends to be a lot more repeatable than if you try to go down to where that vapor pressure versus volume curve is really spiking up. So on the transmix side, this one might be a little bit difficult to see, but at the bottom here, you can clearly see the difference between a gasoline spectrum and a diesel spectrum. In our model space, you can see we have two distinct clusters of data. This is what gasoline looks like. This is what diesel looks like. And what we do is we can use the analyzer to say, and this is where the two products are mixed together and is not on spec for either gasoline or diesel. Truck and rail, so real-time composition of data of fluids, as I showed, sort of going onto rail cars or onto truck terminals. So one analyzer can be measuring at each truck bay. Just put multiple fibers out there. I'm going to come back to the calibration frequency question in a minute.
Great, thanks.
So I'm close to wrapping up here. Actually, I'll do it right now. So no, we don't do an actual calibration. ever. We measure spectra, we look at how well they're matching to the model, we pull a lab sample and compare it to how the analyzer is reading to validate that the model is still working. Currently, I don't know of, and again, JZ, you're going to know, or Greg, you may know, I don't think there's one where we've actually put a calibration cell in there. So many custody transfer type applications are determined by what the lab gets, that we sort of feel like the best thing to do is always compare our results to a lab result and then say, okay, are we matching the lab? If so, we're golden. So we're getting really close to the end. So what next? So we've talked about applications we do commonly, talk about things we can do. And if you've got questions, contact us. I'm going to put up some contact info at the end. We're currently doing multiple applications across, all the major basins in North America, but we certainly are aware of there's more applications for this technology. So we can put these anywhere pretty much across the hydrocarbon processing industry, certainly from natural gas liquids, crude and refined fuels, and a lot of the fractionation fluids that we make from those. Just like to acknowledge a few things. So I guess first really I should acknowledge JP3 and Flotek for giving me the privilege of being able to present this to you guys. It's really an honor, and I enjoy public speaking, and I think they kind of know I like doing these, and so they say, oh, we'll let Phil do it. He's okay with that. I'd like to thank all of you for joining us. What makes these events great is when we get a good turnout like this, and we get a lot of questions like this. I love the fact that we've had a lot of questions, certainly willing to address more at the end. Making Measurements Matter, of course, and Chelsea's team, they do a fantastic job of advertising these things, of promoting these things, and helping us get the word out to people. So, you'll probably see, you're going to get emails from us again as we do other webinars. And we're bringing in a whole thing where we're actually going to try to get customers to do webinars, bringing in a thing called Nerd Talks, but basically getting customers to say, I have a problem. Anybody, this is a problem measurement I have. I'd like somebody to help me find a solution. And of course, Chelsea Dalzell Creative and her team has done all that website building for us as well. So again, a big thank you to them. As far as contacts, I'm just going to leave this up at the end. If you're looking for more information, Mohit, who is on the call, is in the Middle East. Greg is in the US. I'm in Canada. Feel free to contact any of us, and we'll be happy to try to get you more information.
Okay, so we have gone a little bit over time, and there are still some questions in the chat. So I'm going to go ahead and address them with you, for you.
Okay.
And anyone that needs to jump off, obviously, feel free to. Thank you again, everyone. Thanks for being here. Thank you for going a little bit over time with us. And I'm just going to go get to it with a few of these questions. Now, we've got some good feedback too. Yay, you, Phil. Okay, now what do we have here? Do we have any existing installations for custody transfer?
Yes, certainly for custody transfer of fluids, yes. I mean, so actually, this is an interesting question. So often the custody transfer agreement is written around the lab samples. What we have is a lot of analyzers that are being in place looking at custody transfer applications, monitoring product quality, helping people optimize their process, and trying to say, I'm going to, in Canada, for example, we have a specification, you have to be less than 5% butane in our condensate. So a lot of our clients are using this to either optimize their condensate stabilizer and staying as close to that 5%, or blend butane in and getting up close to that 5%. They use the analyzer to ensure they will meet the custody transfer agreement, but the custody transfer agreement is sometimes still written around lab samples. So hopefully that addresses that question.
Brilliant. Okay, and then it looks like we have a whole bunch of feedback. Thank you. Excellent presentation. Looking forward to connecting and speaking more. Brilliant.
Okay, there's one about competitive position against MKS. So that was for Lesh, I think. So MKS is another near infrared another infrared technology. MKS, as far as I know, is still 100% gas phase measurements only. And so the difference is, again, for us, we've been, for certainly us in Canada, liquids applications is where there's been a lot more money to be spent or made. NGLs and condensates, crude oil blending. So competitive position is probably that their competitors, like other people are, on the gas phase side, and not at all of a competitor as far as I know on the liquid phase side.
Okay, thanks. And does anyone else have any questions that they want to hop off mute and actually ask Phil yourself? Now is a great time for that, everybody.
We have another one here, it looks like from Daddy. Hey, Daddy, how you doing, man? JP3 open market for Asia Pacific. Again, our install base right now is in North America. So one of the purposes of this presentation was to let people know about the technology in different market segments and start being able to look at applications. And yeah, we have some nice comments in there. Thanks very much for those who are putting those in there. Appreciate it.
All right. All right, everybody. Well, if there isn't anything else, if Phil, do you have anything else that you wanted to say? Thank you, everybody. Thank you.
Again, just thanks, everybody. It's been a really enjoyable presentation for me. I like when we get a lot of questions. It brings so much more out, I think, for all the participants. So I really appreciate the fact that there's been that level of interaction. It's been great. And hey, Ravi.
There is one hand up.
Yeah.
Phil, do you hear? I think that was a mistake.
Okay.
All right, everyone. Well, thank you very much for joining us. Thanks from all over the world for joining us. Thank you so much, JP3, Phil, team, everybody that's here with us today. We will make sure to get an email out to you with a whole bunch of information. And thank you for all your questions and comments and requests. We'll make sure that everybody gets the information that they need and make sure that everyone is very easy to find.